Hello everyone, I'm Omidi, a PhD student in Laval University in Quebec, Canada, at the Center of Optics, Photonics and Lasers. Today I'll be talking about the geometric constellation shaping using initialized autoencoders. I would like to acknowledge my co-authors, Professor Zheng from Laval University, Dr. Lin from Hawaii, Canada, and Professor Raj from Laval University. My presentation will start with an introduction about geometric constellation shaping and a deep neural network-based machine learning technique called autoencoders. Then I will talk about the autoencoders as end-to-end communication system, and I will explain the architecture of proposed initialized autoencoder used for geometric constellation shaping and will present an example of the training process. Resulted constellations and performance evaluation will be discussed next. At the end, I will give conclusions and future works. Constellation shaping is a technique to boost the transmission capacity and can be either geometric or probabilistic. Geometric constellation shaping optimizes the locations of the constellation points in the complex plane to achieve more compact constellations with reduced peak and average power. Here is an overview of some QAM constellations as the result of conventional optimization methods. The basic QAM constellations are the well-known square QAM used for even power of 2 constellations and rectangular QAM used for odd power of 2 constellations. XQAM or cross QAM is the alternative constellation for rectangular QAM to reduce the average power by moving 2 columns of points from left and right to top and bottom. Star QAM comprises of multiple concentric phase shift keying circles, each with an equal number of constellation points and equal phase angles, which are preferred in systems limited by peak power. And HQAM or hexagonal QAM in regular and irregular forms targets maximizing the minimum separation between 2 neighboring points, thus placing the constellation at the center of an equilateral hexagon. IHQAM or irregular hexagonal QAM constellations are set symmetric around the origin to achieve more compact packing. Recently, machine learning techniques have attracted much attention for optimizing constellation shaping. Among the different machine learning techniques, autoencoders have shown great potential for constellation shaping. They are unsupervised deep learning techniques that are used to learn efficient data coding. Autoencoders consist of 2 main parts named encoder and decoder. Encoder is a fully connected deep neural network that maps input data to a compressed presentation called code. And decoder is another deep neural network that reconstructs the input from the code at the output layer. In our application, input and output will be the bits or symbols, and code will be IQ coordinates. So, how can we use the autoencoders as end-to-end communication system? In this case, the structure is almost the same as the regular autoencoder, with some changes in the code layer. We can see that the encoder and decoder structures are almost the same. But in the code layer, power normalization and channel effects are applied to the output of the encoder, and then noisy IQ coordinates are fed into the decoder part. So, 3 main blocks of a communication system, which are transmitter, channel, and receiver, can be seen here. And now I will explain the training process of autoencoder as end-to-end communication system in more details. In this structure, first the input of the autoencoder is formed in either one hot vector or binary symbols. There will be a discussion about the types of inputs at the end. The input data go through the encoder layers to generate the IQ coordinates. Then power normalization is applied. Then noise effect is added to them, and finally the decoder tries to reconstruct the input data from the noisy IQ coordinates. The output of the decoder is a vector of scores, which has positive and negative values. These scores are then compared to the input data to calculate the loss, which is used in backpropagation process. This process is done iteratively until we catch the preferred result. To be able to get the output in shape of ones and zeros, we need to change these scores to the probabilities. This can be done with softmax or sigmoid function, which is chosen based on the type of input. For our case that one hot vectors are considered as the input, softmax is applied and a vector is generated which sums up to 1, as it can be seen in the example. Then the maximum value will be considered as 1 and other entries would be set to 0. Now let's see why we employed deinitialization. Constellation shaping is a non-convex problem, and as we know, in non-convex problems, finding the global optimum point besides several local optimums has always been challenging. One of the methods to deal with such problems is to try to start the optimization process from somewhere close to the global optimum point. This can be achieved with initialization so that we will be able to get the global optimum. For this problem, we can use non-constellations like square QAM and IH QAM as the initializers. So based on what was explained, the architecture of the initialized autoencoder can be seen in this figure. The end-to-end communication system block was explained previously, but for the initializer block, we need to first decide what initializer to choose. In this scratch, IHQAM is chosen. Then a fully connected feed-forward neural network with the same structure of the encoder in the autoencoder is created and trained to map the given symbols in one hot forms to IQ coordinates of IHQAM. And the same thing is done for the decoder part, and a fully connected feed-forward neural network is generated in a way that it can map any symbol in IQ form to its one hot representation without any error. Finally, the generated initializers are copied on the encoder and decoder parts of the autoencoder, and the main training process starts. Here is an example of the explained initialized autoencoder for geometric constellation shaping. First, the encoder initialization starts and it tries to reconstruct the IHQAM or irregular hexagonal QAM as the first step. And then decoder initialization starts at the second step. Now it is being done in the background. After that, these are copied in the autoencoder and the main training process starts. This is just some frames of the whole process. In real execution, it usually takes too long. The simulation is done for optimization of 64 QAM over the AWGN channel. Both square QAM and irregular hexagonal QAM or IH QAM are considered for the initialization. and the results are quantified in terms of bit error rate and symbol error rate with a Monte Carlo simulation by counting at least 100 errors. And implementation is done in Python programming language, and PyTorch is selected as the deep learning framework. And the training parameters are listed in the table, and you can see. Shaping results can be seen in these figures. In left column, IHQAM in top and square QAM in bottom are presented as the initializers, and in right column, resulted machine learning based constellations generated with each initializer are presented. As it can be seen, the constellation initialized with the IHQAM has maintained the original structure and made small changes to improve it. These four constellations will be compared in terms of symbol error rate and bit error rate. Here, symbol error rate vs EB over N0 plot is presented for the constellations shown in the previous slide. The red curve is related to the machine learning initialized with IHQAM. Mauve dashed curve is related to the machine learning initialized with square QAM. Blue dashed curve is related to the square QAM, and black curve is related to the IHQAM. As the first result, we can see that both machine learning based constellations outperform their counterparts. More precisely, a performance gain of 0.18 dB and 0.39 dB can be achieved for IHQAM and square QAM respectively. This shows the effectiveness of applying machine learning methods. And the most optimum result, which is obtained when initializing with IHQAM, can achieve a performance gain as large as 0.47 dB compared with square QAM. And here we have the bit error rate performance. We can see that the proposed scheme initialized with IHQAM outperforms conventional IHQAM for any EB over N0. For square QAM, there is a trade-off between enhancement in packing and bit mapping. As mentioned in symbol error rate performance, machine learning initialized with square QAM outperforms the conventional square QAM. But when looking at the bit error rate performance, square QAM acts better than the machine learning based square QAM or the machine learning algorithm initialized with square QAM. And this is because the square QAM has better bit to symbol mapping than the machine learning based approach. As we mentioned, proposed method gives the improvement in terms of symbol error rate, and it doesn't consider the optimization of the bit to symbol mapping. The solution for this problem in literature is to consider binary symbols instead of one-hots as the input of autoencoder. In this figure, A, B, and C are generated with binary symbols as the input, and D is generated considering one-hots. In all three constellations generated with binary inputs, a gray-like code is formed for the constellation, but the shaping performance is worse. Whereas in the constellation generated with one-hots as inputs, we have a more symmetric constellation with no optimized bit to symbol mapping. So optimization of the bit to symbol mapping and consequently bit error rate performance within the machine learning method is still challenging. As a conclusion, we compared constellations generated by autoencoder initialized with the conventional square QAM and IHQAM. The best results were obtained when machine learning was initialized with IHQAM and 0.47 dB gain was obtained compared to conventional square QAM, and 0.18 dB gain was obtained compared to the conventional IHQAM. For the future works, as mentioned, bit to symbol mapping problem is not addressed within machine learning solutions. By addressing this problem, we will be able to improve bit error rate performance as well as symbol error rate. At the end, I would like to acknowledge that this research was supported by the Huawei NSERC Industrial Research Chair and by NSERC through its Discovery Grant. And thank you for your attention.